You start yours. Okay, so it's a great pleasure of Wilbur Shirley, and he'll continue on the theme of lattice, um, obstructions, anomalies, and talk about his recent paper on anomalies gauging and on-siteability. So please take it away.
Yeah, thank you. And thanks to all the organizers for inviting me to speak. It really is a pleasure to contribute to this series. Um, so I will presume that this particular audience does not need to be convinced about the importance of studying generalized symmetries. Um, but today, my talk will be from the perspective of Hamiltonian lattice systems, and in particular, sort of the overarching goal that I have in mind is to systematize the understanding of generalized symmetries on the lattice. So there's at least a couple different reasons why one might want to do this. Um, First of all, the the lattice setting provides a context in which these ideas can be explored in a very concrete and precise way. Um, Moreover, if one wishes to study topological phases of lattice systems from the perspective of generalized symmetries, um, as is sort of in fashion these days, then certainly one first needs a firm understanding of how this all works on the lattice. Um, and so this sounds like a very reasonable goal to have, but let me say a little bit more in detail about exactly what I mean by this. Um, so first and foremost, um, one would certainly want to be able to define what one means by uh, a generalized symmetry. And I think we can all agree that a symmetry is some set of operators that commutes with a Hamiltonian of interest, but we wouldn't say that any any set of operators constitutes a symmetry. There should be some physically reasonable properties that some set of operators should satisfy in order for it to be considered a symmetry. And really, I would say that um, we have a satisfactory operational definition really only in the simplest of cases. Second, we would like to have some set of tools that we can use to characterize a given symmetry. So, for instance, among other things, we would like to be able to diagnose systematically the anomaly of a given symmetry. Third, we would like to have some appropriate notion of equivalence uh, of different symmetries. So, in particular, we would like to be able to compare different symmetries acting on the same system, or even more generally, we would like to be able to compare different systems and symmetries acting on different systems. And we would like to be able to say when two sets of symmetries are equivalent in some sense. And lastly, if we have some notion of equivalence, we would like to be able to have some classification. So what are the set of equivalence classes? And probably should add this to the list, but perhaps it goes without saying that we, of course, would certainly like to also understand consequences of the presence of some particular symmetry. Um, so this is this is really a quite a gargantuan undertaking, and certainly I will not achieve this in its entirety in this talk. But what I will do is basically explain how this all works in sort of the simplest possible case. Um, so in particular, I will focus on discrete invertible symmetries and really the simplest such kinds of symmetries. So in particular, I'd like to talk about zero form symmetries in 1+1D and one form symmetries in 2+1D. Um, and what these have in common is that their defects are point-like objects in space, and this will this will actually make these two kinds of symmetries amenable to something of a unified treatment. And along the way, we'll also be able to extrapolate some more general lessons about both ordinary zero form and as well as higher form symmetries in general space-time dimension. So the talk is based on the paper from earlier this year with Sahand, as well as another paper which is forthcoming and hopefully will hopefully appear in the next couple of weeks. There's also been several related works by other authors, and the results are largely in agreement. Okay, so are there any questions so far? Or so good? Okay, so yeah, so okay, so I'll start with the discussion of zero form symmetries in one spatial dimension, and so let me just give the basic setup. So I will exclusively work with a tensor product Hilbert space. And for simplicity, let's assume that the on-site Hilbert space is always finite dimensional. So I'll consider some finite group G and say that a zero form G symmetry is a homomorphism from the group G to the group of QCAs. So these are locality preserving automorphisms of the operator algebra, um, or in other words, these are some locality preserving unitary operators, and denoted by UG. Okay, so let me begin with the definition of this sort of a new term. And so we say that a G symmetry is on-sitable if it can be transformed into an on-site form by conjugating by some finite depth circuit. And in this definition, I will always allow for the addition of some ancillary degrees of freedom that transform under some on-site G symmetry. So physically, ancillas can be thought of as representing some highly inert degrees of freedom that are sort of lurking throughout the system, and so it's eminently reasonable that um, we should sort of allow for the addition of ancillas in this definition. So um, as an equation, we start with our symmetry U. We tensor potentially with some on-site symmetry X, conjugate by the circuit W, and we end up with some other on-site symmetry Y acting on the composite system. If this is possible, then we say that our symmetry is on-sitable. Okay, so it's very well known by now that in 1+1D, G symmetries are characterized by an index valued uh, in the degree 3 group cohomology, and this index, of course, represents the anomaly of the symmetry, and really can be thought of as like the F symbol of the symmetry defects, and this is the so-called L-Snijak index. And so the claim that I make is that a 1D G symmetry is on-sitable if and only if its L-Snijak index is trivial, and this is what I will show in explicit detail. And so let me just mention that one direction of this claim is sort of obvious because if a symmetry can be made on site, then it clearly must have a trivial index. And so it's really the other direction that is not trivial, to show that if the index is trivial, that we can sort of explicitly make the symmetry on site. Okay,
Hi,
so what is
Wilbur. I have a quick question.
yeah.
Do we have any assumption on the Hilbert space? Does it require to be a G-spin, or can it be a larger ancilla?
We allow any kind of ancilla. The ancillas should be, themselves a tensor product Hilbert space, but it doesn't have to be a G-spin.
But does it on-siteability depends on the degree of freedom? So for example, the semi-online is not on-site using Z2 qubit, but in our Z4 construction, somehow it can become Pauli of X and Z using Z4 qubit. So is it a property depending on the underlying Hilbert space?
Um,
Well, that's a Z4 symmetry, right? If you embed into Z4 qubit, semion becomes Z4 symmetry.
Yeah,
And
but
if
we can
you
design a
have more
harmonic that state order two.
it's about symmetry, like it's a Z4 symmetry, not Z2 symmetry.
Okay, I see your point.
Yeah.
so one comment I can make is that in general, the sort of, allowing for ancillas is important in this classification. There's a very simple example, which I'll actually discuss later, this so-called CZ symmetry, which is anomaly free, but cannot be made on site if you don't allow for ancillas at all. And so it certainly is the case that the kinds of ancillas that you allow will impact the classification. But for my purposes, I'm always going to allow arbitrary ancillas.
Okay, thank you.
Mhm. Okay, so what's the strategy here? So basically, the strategy is to utilize a reformulation of the anomaly index, which was given in the work of Saif Nashri. And so let me explain how this works. So okay, so the first thing that we'll do is sort of we'll work with a so-called mesoscopic lattice, lambda. And what do I mean by mesoscopic? Well, the symmetry operators have some spread or range, and basically we want to choose our mesoscopic lattice so that the spacing is at least greater than the spread of the symmetry operators. And so we're sort of zooming out sufficiently far that sort of microscopic details of the symmetry operators are not so important. And henceforth we'll sort of always just think in terms of this mesoscopic lattice. So what do we do? So for each group element and each point of this mesoscopic lattice, what we do is we choose a restriction of the corresponding symmetry operator to the left of the point J. So by restriction, what I mean is that this operator UG comma J, it acts like the symmetry UG to the left of J, and it acts like the identity to the right of J. What it does precisely near J is sort of it's sort of ambiguous, but sufficiently far to the left, it acts like the original symmetry, and sufficiently far to the right, it acts like the identity. Physically, this restricted symmetry has the interpretation of basically inserting a G defect at point J. So more specifically, it sort of brings a G defect in from left infinity. Okay, then what we do is we consider this particular composition of restricted symmetries. And what this combination does essentially is, if we imagine that we start with a G defect at point J minus 1 and an H defect at point J, then what we do is we annihilate this pair of defects and bring in the composite GH defect at point J. And so this sort of composite operator is necessarily supported near the interval J minus 1 to J. And so it's in particular, it has some local action. Therefore, it equals the adjoint action of some local unitary operator, which we call a fusion operator. And we sort of use this diagrammatic notation to denote the fusion operator, right? And so, this diagram has the interpretation of, all right, we start with a G defect here and an H defect here, and then we fuse them together into a GH defect. Now, sort of the crucial point here is that the overall phase of this fusion operator lambda is inherently ambiguous because the defining property of lambda is that its adjoint action is the same as this composite operator, and so the overall phase is inherently ambiguous. Okay, so then what do we do? So what we're going to do is to define the F symbol in terms of these fusion operators. And it will be convenient to use this sort of diagrammatic formalism to keep track of what's going on. So, okay, so how do we interpret this sort of diagram? Well, basically, each diagram is itself a local unitary operator, which is some composition of fusion operators. And basically, the way this works is that each layer is itself a unitary, and then when we take a vertical stack of layers, we just compose the individual unitaries. And we sort of denote this vertical line just denotes the identity, right? So this first layer, this is just this fusion operator lambda J of H comma K. And we sort of represent an identity defect by the absence of a line. So for instance, this operator here is this lambda J minus 1 of G comma 1. Right? Okay, so what we do, right? So we consider these two unitary operators, and we observe that they have the same adjoint action. They correspond to the same automorphism, and therefore the unitary operators must be equal up to a phase. And so this phase, we give it a name, and I'll call it little f. And this little f is a function of three group variables GH and K. And let me just mention that sort of in these diagrams, the convention is that sort of the final fusion outcome is sitting at point J. So it's not drawn, but here this line here is at point J, and likewise over here. Okay, so right, this diagrammatic formalism is just a convenient way to sort of represent equations involving products of fusion operators. And so this equation is just the diagrammatic version of this equation here, right? So there's 5 fusion operators and then the phase little f. So the little f is not quite the anomaly 3 cocycle. We have to use just a little bit of a trick to actually extract the actual f symbol. And so what we do is we just pick some point J, some reference point, and then define the f symbol to be some particular ratio of these little f phases. This is some trick that Sahand invented. Right, okay, so we had better check that this sort of all makes sense. So the first thing that we need to check is that this f symbol is actually a 3 cocycle, and in particular, it had better satisfy the pentagon equation. And in order to do this, we just sort of we start with this unitary operator here to the left. And what we're going to do is use the definition of little f to equate this operator here with this operator here sort of in two different ways. And so in doing so, we get an equation. We get some constraint on the little f's, and then based on the definition of big F, it's not hard to show that this sort of modified pentagon equation for the little f's actually implies the actual pentagon equation or the three co-cycle condition for big F, which of course is a function of three group variables. Okay, so indeed we get a free co-cycle, but additionally, right, we're doing group cohomology, so there should be some gauge equivalence at play, and basically this arises because of the ambiguity of the overall phase in each of these fusion operators. And so in particular, if we transform this overall phase by some two cochain nu, then we find that the F symbol transforms by some particular co-boundary, which is this ratio of these new phases. Okay, so this is all to say that indeed we define a three co-cycle in this way, which is denoted by F. Okay, so then what we would like to do is basically show that if the anomaly index is trivial, that we can actually gauge our symmetry. And so in particular, so the first thing that we do is we sort of make some judicious choice of the phases of all the fusion operators in order to basically uniformly set these F symbols to the identity. And so basically we get this equality, and we can sort of freely equate these unitary operators. Okay. So if we want to gauge our symmetry, we sort of follow the typical prescription. So first, what we do is we expand the Hilbert space to include some gauge degrees of freedom, and so in particular, we add a G-valued to each site of the mesoscopic lattice. So ordinarily, gauge degrees of freedom go on the links, but here we're sort of working on the dual lattice, where our mesoscopic lattice points are sort of labeling locations of defects. And so really we think of the gauge field as some configuration of defects, and so it's appropriate to put the gauge degrees of freedom on the sites of this mesoscopic lattice. Then what we do is we use the fusion operators to define a Gauss's law operator as in this way, and we impose the constraint that all these operators are equal to the identity. And sort of the crucial point here is that because of this equality here, we have that the Gauss's law operators form commuting G representations. And this is obviously necessary if we want to simultaneously impose that they all are equal to 1. And then if we have some Hamiltonian that we would like to gauge, well, the gauged Hamiltonian has this form, where this H here is basically some defect Hamiltonian that's obtained from the original Hamiltonian by insertion of this configuration of defects. Okay, so this is all very nice. What does this have to do with onsiteability? Well, basically, in order to disentangle an anomaly-free symmetry, what we'll do is we'll make use of these so-called modified Gauss's law operators. So now what we want to do is consider a different expanded Hilbert space in which we instead of tensoring in some gauge field degrees of freedom, what we instead do is tensor in some ancillary spins. These ancillary spins will live on the links of our mesoscopic lattice, and each of these is itself a G-valued degree of freedom. So the this ancillary Hilbert space of G spins sort of has a natural on-site G symmetry, which is just left multiplication by left multiplication on simultaneously on all of the ancillary spins. And then what we do is we define these so-called modified Gauss's law operators, which are also defined in terms of these fusion operators, but sort of include the action of right multiplication by G inverse on the ancillary spin on this link L. And basically, what we get from the fact that the original Gauss's law operators form commuting G representations, we get sort of automatically that these modified Gauss's law operators also form commuting G representations. And then what we can do is actually define an explicit disentangling circuit in terms of these modified Gauss's law operators. And so basically this circuit W can be thought of as some unitary on the original matter degrees of freedom that is controlled by the configuration of ancillary G spins. And so this is some sort of formal definition, but what one can show sort of straightforwardly using some simple algebra is that these properties of the modified Gauss law operators, in particular, that they form some commuting G representations. What one can show is that this W is indeed a disentangler for the symmetry U. In particular, U tensored with this left multiplication, when conjugated by the circuit W, we're left with just the left multiplication on these ancillary spins. And so what we've done is successfully transform our anomaly-free symmetry into an explicitly on-site form. Okay. Okay, so this is, it's a little bit abstract, but just to be concrete, let me sort of explain how this works for a very simple example. And so this example is this so-called CZ symmetry. So how does this work? So we consider a qubit chain, and we consider this Z2 symmetry, which is just a product of these two qubit CZ operators on all nearest neighbor qubits. And okay, so basically how this works is that the ancillary degrees of freedom that we add, well, it's simply it's a qubit on each link, and these qubits transform under this global spin flip symmetry. And the disentangler that we define as on the previous slide is this product of control Z operators. So in particular, right, we have this CCZ gate, which acts on a pair of matter qubits and the ancillary qubit on the link in between these two sites. And the action of CCZ maps, this product of X with CZ to just the X operator. And so what we find is that this W is indeed a disentangler for this CZ symmetry. Okay, so let me sort of summarize by sort of just discussing the sort of overall relationship between these notions of anomalies and gauging and unsightability, right? So okay, so for the sake of discussion, let me define a G symmetry to be anomaly free if it admits a symmetric gapped local Hamiltonian with a unique invertible ground state. And so it's known that a symmetry is anomaly free if the H3 index is trivial. And basically the upshot of this discussion is that in 1+1 dimension, we have a complete equivalence between these three properties. So in particular, a G symmetry is anomaly free if and only if it can be gauged, if and only if it is unsightable. Okay, so this is sort of a very nice story. In 1+1 dimension, what one might ask whether this generalizes to higher dimensions. And basically, the sort of the construction of the disentangler in terms of Gauss's law operators and modified Gauss's law operators is some very general argument that doesn't depend on the dimensionality, and so we can claim in generality that the conditions of gaugeability and on-siteability are equivalent in general. However, these conditions are stronger than the condition of a symmetry being anomaly free. And I won't discuss this in detail, but we know this because of the construction of some particular examples of symmetries that admit some trivially gapped Hamiltonian, but are themselves not unsightable. There's some obstruction to unsightability. So we find that this is sort of how the relationship between these three concepts works in dimension above 1. Okay, so let's see. Before I move on to talk about higher form symmetries, let's see. Are there any questions at this point? Okay, no questions. Good. Okay. So now let me move on and talk about higher form symmetries. Okay. So, okay. Okay. So okay. So I'll continue to work exclusively in the context of a tensor product Hilbert space. Obviously, there are many models of interest which are not captured in this setting. For instance, if we want to talk about some kind of gauge theory or some other kind of Hilbert space with some constraints, then obviously that's not a tensor product Hilbert space. But for simplicity, I'm just going to continue to work in this setting, and I'll consider a finite abelian group A. And so, the first question to answer is what precisely is meant by a higher form symmetry on the lattice. And basically, it will be very convenient to sort of use the machinery of cellular homology to discuss the notion of a higher form symmetry on the lattice. And so again, we're going to sort of consider some mesoscopic lattice, which is larger than the sort of microscopic spread of the symmetry operators. And what we're going to do is consider some cell complex and consider the sort of the cellular chain complex with coefficients in the group A. And so we'll denote the group of n chains with A coefficients by this notation here. And so we will define a p-form symmetry on the lattice in the following way. So we'll say that a lattice p-form symmetry is a homomorphism from the group of d minus p cycles to the group of locality preserving unitaries and satisfying this condition. So in particular, the unitary corresponding to some cycle should be supported, in the vicinity of the support of that cycle, which is sort of what I mean by this chi of C here. So this is sort of a reasonable condition to impose, and this definition is, to my knowledge, first appeared in this work by Chi, Radzahovsky, and Hermle. Okay, so this is our operational definition. So next, basically, I want to define two notions of onsiteability of higher form symmetries.
Excuse me, may I interrupt for a second?
Yeah, please.
What's the motivation for defining higher form symmetries the way you define them? Because these things usually people say that there are no higher form symmetries with a tensor product Hilbert space, and that this definition, it doesn't really reflect what we expect of a higher form symmetry, because it does not ensure that it's that the transformations are topological, because you don't require the transformation, like the unity, not to depend on the homology class, right? To depend on the on addition of exact chains to this chain. So it's some different notion from what we usually call higher form symmetry in field theory.
Yeah, so I would say this is sort of a notion of like a microscopic or a non-topological higher form symmetry.
Because basically saying that, probably in the back of your mind, like if you have like tensor product Hilbert space, you don't have genuine higher form symmetries. They have like a choice to make. Either you work with non-topological higher form symmetries, or you work with, or you abandon the tensor product Hilbert space. So you choose to do the former.
So here, yeah, I'm certainly choosing to do the former. As far as motivation, one could imagine that one has some 2D topological order, say, and you want to consider some string operators for the anyons of that topological order.
Okay, so yeah, I understand, but I just want to make sure you understand that this is not the usual the field theory notion of
yeah, that's right, and that's right, and so that's sort of why I sort of say that this is sort of what I call a lattice p-form symmetry. Okay, so this definition sort of lends itself very nicely to then defining these notions of onsiteability and so-called higher onsiteability. And so, okay, so first of all, I'll say that a p-form symmetry is onsitable if it is basically equal to the restriction of another homomorphism V, which is from the group of all D minus B chains to the group of locality preserving unitaries. Okay, and it's not hard to see that this definition sort of directly generalizes the notion of onsiteability for zero form symmetries. And of course, as per usual, I'm sort of allowing for the possible addition of some ancillary degrees of freedom in these definitions. Okay. Secondly, let me introduce this notion of Q onsiteability. So let Q be some number less than or equal to P. Then we say that a P-form symmetry is Q uncitable if for any codimension Q submanifold, the P minus Q form symmetry U composed with the natural inclusion is onsitable as a P minus Q form symmetry acting on the spatial manifold N. This is a very natural a notion to consider. Yeah, basically we're sort of saying that we sort of restrict our consideration to this submanifold N and then apply the notion of onsitability to the symmetry that we get by restricting to the submanifold N. Okay.
So can I ask a question?
Yeah.
So do you want to consider a setup where the some symmetry operator itself looks on site, but its junction is not on site, something like that? If we consider P onsitability, symmetry operator itself looks on site in the bulk, but its junction or some higher codimensional locus doesn't look on site, something like that. Maybe my
I'm not sure I follow.
Sorry. Yeah, maybe. Yeah, never mind. Yeah, well, I just wanted to understand what's the difference between just onsitability of the high horn symmetry and this P onsitability.
Yeah, so basically we basically you sort of restrict your consideration to this submanifold N, and sort of when we restrict to N, we get some symmetry that acts only on the manifold N, and we can then ask whether the symmetry is onsitable as a symmetry acting purely on the submanifold N. And so
so sorry, dimension of the submanifold is the dimension of the submanifold is larger than the dimension of the symmetry operators?
That's right. Yeah, that's right.
Well, in this case, let me see.
It's
What are the
codimension Q.
Yeah, I understand. But then what's the difference between just onsitability and P onsitability? Q onsitability? I don't really follow because the symmetry operator is completely embedded in the codimension Q manifold, submanifold. No, so I'm a bit confused.
Well, a symmetry can be Q onsitable, but not onsitable. Okay, so
maybe.
I think maybe this will be clear when I sort of discuss in the context of one-form symmetries in 2+1D. I think hopefully that should clear up any confusion. So yeah. So, okay, yeah. So these are some general considerations about higher form symmetry, but but now let me specialize to the case of one-form symmetry in 2+1D. Okay, so just for simplicity, let's just work with a square lattice cell complex, and when we do this, basically a one-form symmetry with group A is generated by an operator U, A, comma F for every group element A and face F of the square lattice, right? And these generators should satisfy some simple properties. So obviously they should satisfy the group law for a given face. All of these generators should commute with one another, and crucially, if we take the product of all of the U's over all faces for a fixed A, we should get the identity, right? And so just as a simple example to have in your mind, the string operators, the closed string operators of the toric code constitute a Z2 times Z2 one-form symmetry according to this definition. And of course, the defects of this kind of symmetry are point-like objects in space. Okay, so obviously it's sort of well known that the anomaly of a one-form symmetry in 2+1D is fully characterized by the topological spins of the defects, and so this is some quadratic form from A to U1. So obviously the paradigmatic example would be some anion excitations of some gapped 2D topological order. Now it's been known for 2 decades now how to compute the anomaly of such a symmetry using this so-called T-junction process. So this is sort of very well known and established, but for the purposes of what I'd like to do here, we need something a little more refined. Just this quadratic form is sort of insufficient for our purposes, and so really what we really need to look at is the F and R symbols. Maybe it's not super well known that the F and R symbols for abelian anions sort of can be thought of as forming some equivalence class of a cohomology theory, and this is distinct from the ordinary cohomology, but it's some cohomology theory which is called abelian cohomology. It's denoted as H subscript AB, and this originally goes back many decades. And okay, this is just some repackaging of what we know about F and R symbols, but basically an abelian 3 chain is a pair of maps F and R, and such a pair of maps is considered to be a abelian 3 cocycle if the pentagon and hexagon equations are satisfied, and such a pair of maps is considered to be a 3 co-boundary if there exists another map U from A times A to U1, such that F and R are these functions of the map U. Okay, so this is just saying that F and R symbols can be given some equivalence relation, and the equivalence classes form the elements of this abelian cohomology group. Okay, and it's established in this original work that as we should expect, the equivalence classes are in one-to-one correspondence with the quadratic forms on A valued in U1. Okay, so it's just some repackaging of what we all know. Okay, so what I'd like to do is sort of basically generalize or maybe analogize the analysis that I discussed for zero-form symmetries in 1D, and sort of adapt that analysis to this new setting. So okay, so what we do is we have our mesoscopic lattice, And what we're going to do is first of all is sort of define the analog of the restricted symmetries that we made use of in the 1D setting. So in particular, we're going to want to define two sort of defect insertion operators. So the first inserts defect from the negative x direction, and the second from the negative y direction. And these two operators are not independent of each other, but have to sort of insert the identical defect, which just means that if you sort of compose these operators with one another, then this composition should look like it should look like a one-form symmetry operator in the vicinity of point J. Or more specifically, right, if we take the inverse of this and compose it with this, then, right? So okay, so and then what we do is we sort of we play the same sort of game. We want to define fusion operators as some composition of these defect insertion operators, and so basically for each x-oriented link and each y-oriented link, we're going to define a fusion operator, which sort of is interpreted as fusing an A and a B defect together into an AB defect. And basically, the convention in these diagrams is again that the sort of final fusion outcome is located at point J, but now obviously we're in 2 dimensions, so we sort of have to keep track of where the defects are in 2-dimensional space, and so we'll sort of basically use this trick. So sort of in this diagram, this A lives at point J minus X, B lives at point J, but in this sort of Y-oriented fusion operator, this A defect is sort of interpreted as living at point J minus Y, and this B lives at point J. And so we sort of use this diagonal line to imagine that this A defect is sort of being moved into the screen to join up with B. Okay, and as in the 1D case, these fusion operators have an inherent ambiguity in the overall phase. Okay, so yeah, so of course we sort of are just generalizing this diagrammatic formalism, and so in particular we'll have to make use of not only fusion operators but their Hermitian adjoints, the splitting operators, which are depicted as such, and so just as an example for how this works, the symmetry operator U A comma F sort of has this diagrammatic representation, and so obviously because we're now in 2 plus 1D, there can sort of be these overcrossings or undercrossings, right? But this doesn't really mean anything. Right, this diagram is just some product of fusion operators, fusion and splitting operators, but just to sort of keep track of, which defect is where, it's necessary to draw these crossings in the diagram. Okay, and basically what we're going to do is play the same game and define F and R symbols in terms of these fusion operators. And okay, so basically to define the F symbol, we do the same thing as we did in 1D. We define this little f, and then we define the actual F symbol as this ratio of little f's. On the other hand, to define the R symbol, well, this is the definition. So it's not hard to see that as automorphisms, right? Or in other words, like the adjoint action of this operator is clearly equal to the adjoint action of this operator. So these two unitaries must be equal up to a U1 phase, and that U1 phase is what we call R. Okay, and okay, so there's a R sub J here, but okay, that's maybe just a typo. Just ignore this. We sort of pick some point J and define the R symbol in this way. And I should mention that the setup is a little bit different, but this sort of method of defining the R symbol is highly reminiscent of this work of Calgo and Levin, these sort of microscopic definitions of anion data. Okay, and okay, so as we did in 1D, so in 1D we showed that the F symbol satisfies the pentagon equation, and now we sort of have F and R symbols, and so they should satisfy not only the pentagon equation but also the hexagon equations. And so let's do that here. So the idea is very similar. We sort of begin with this somewhat complicated diagram here, which represents some unitary operator, and then we use these equivalences to equate this operator here with this operator over here in two different ways. And sorry, I actually said that this J was a typo, but it's actually important that we sort of keep track of where we're sort of doing this R move. Yeah. So let me not get too bogged down in the details, but basically, what we do is we sort of derive this sort of lattice version of the hexagon equation in terms of these R's and little f's, and then basically it's not hard to show that this sort of lattice equation implies the sort of the actual hexagon equation that we would like to have. And so here this R is basically the R associated to some particular point J. And again, sort of in all of these diagrams, the convention is that this final fusion outcome occurs at point J. Okay, so indeed we find that this definition gives symbols which satisfy this hexagon equation, and we can do something very similar to obtain the other hexagon equation. Okay, and so so we have that F and R satisfy the pentagon and hexagon equations as they should, but right, there's also this sort of gauge freedom, and it's very straightforward to see that under a change in the overall phase of the fusion operators, the F and R symbols transform as they should. In particular, in this way, where U is some function of these phase factors here. And so the upshot is that we're able to define these F and R symbols that constitute an equivalence class of this degree 3 abelian cohomology. Okay, and okay, so what we can do using this is show that if the F and R symbols can be trivialized, then we can gauge our one-form symmetry in a manner very similar to what we did in 1D. So in particular, we expand the Hilbert space by adding some gauge degrees of freedom. We define Gauss's law operators in terms of these fusion operators, and then define some gauged Hamiltonian to be of this form, where this Hamiltonian here is the original Hamiltonian, but twisted by some defect insertions. Okay. Okay, so that's the sort of ordinary gauging, but what about higher gauging? Well, okay, so obviously there's this notion which is introduced in this work, this idea of higher gauging, and basically we say that P-form symmetry is Q gaugeable if it can be gauged on a codimension Q manifold in space-time. And what's interesting about this notion is that it is not necessary that the symmetry is completely anomaly free in order for it to be higher gauged. So sort of maybe the simplest example would be it's possible to have a Z2 one-form symmetry in 2 + 1D, which is anomalous. In particular, we can imagine that we have some fermionic Z2 symmetry which is obviously anomalous, and yet it can still be one-gauged. And this is possible as long as the F symbols are trivial. So obviously this fermionic Z2 one-form symmetry has non-trivial R symbols, but trivial F symbols, and this allows it to be higher gauged. So microscopically, let's imagine we have some 2 + 1D system, and we have some one-form symmetry that has trivial F symbols. Well, basically, we can just directly use the procedure for gauging zero-form symmetries in 1D to one-gauge this one-form symmetry, right? Because say we have some one-dimensional submanifold, well, we can just treat this as sort of a standalone 1D system and gauge the one-form symmetry operator that sort of lives on this 1D submanifold. And so we sort of get for free that we can do the one gauging so long as the F symbols can be made trivial, even if the R symbols are potentially not trivial. Okay, so the upshot, and hopefully the confusion from earlier will be cleared up. The upshot is that we have the following equivalences. So for one-form symmetries in 2 + 1D, such a symmetry is gaugeable and moreover uncitable if it's anomaly-free. So if the F symbols and the R symbols can be made trivial. On the other hand, as long as the F symbols are trivial, then the symmetry is both one gaugeable and one uncitable. And this does not require the R symbols to be trivial. So, for instance, the fermionic Z2 one-form symmetry that I just mentioned is one gaugeable and one uncitable, but it is not gaugeable or uncitable. And the sort of arguments to explicitly show these facts are, structurally very similar in spirit to the arguments in 1D. We sort of can use these constructions. You can define these modified Gauss law operators and construct a disentangler in sort of the same manner as was done in 1D. And these considerations sort of generalize in the expected way. In general, we can conclude that a higher form symmetry on the lattice is Q gaugeable if and only if it is Q uncitable. Okay, let's see. Are there any questions on this point?
Sorry. So for your definition, like how about the fermion of toric code? Is it for me? It looks on-site because it's a product of the power X and power Z on the on-site operators. Like any loop operator is a product of on-site operators. But in what sense it's not on-siteable? Can you give me a definition of the on-siteability?
Yeah, absolutely. So okay, so let's go back to this definition here. So I would say that the fermionic string operator of the toric code is not uncitable according to this definition. And so what is this saying? That this is saying that this homomorphism U is a restriction of a homomorphism V, which is defined on the group of in this case it would be one chains, right? So what we require is that each symmetry operator can be expressed as a product of unitary operators associated to each link of the lattice, and every one of these link operators they almost commute with one another. And so, the fermionic string operator, as you said, is we can write every string operator as a product of this Z and X, but these, right? So
I see. So here V is some like a map from the open, like a string to some unitary, and you claim that these guys must commute with each other. So
That's
it's yes, I see. So in this sense, fermion is not on-site in this based on this definition. Okay, I understand.
Yeah,
Thanks.
So it's just semantics, really. But yeah, so that sort of brings me to this brief discussion of these other recent works. So first of all, there's this other work which also sort of provides a different solution to unstability of 1+1 to zero form symmetries. Then right, so let me also call attention to this pair of recent works on anomalies and onsiteability of higher form symmetries. So right, so this work sort of defines an anomaly index, which is valued in the ordinary cohomology of this B2G, and really this is presumably fully equivalent to this way of thinking in terms of FNR symbols. I will say that I think this is a very nice way of thinking about these anomalies, because it sort of generalizes very readily to some a more general setting, but I think is fully equivalent to thinking in terms of FNR symbols. And there's this other work which explores the notion of onsiteability and the equivalence with higher gaugeability, and really it's just a difference in nomenclature where what they call onsiteability is what I call one onsiteability, and it's just semantics, really. But okay, so that is pretty much all I want to say. Let me just point out that, as I said in the beginning, there's sort of this overarching goal of systematizing the study of generalized symmetries on the lattice. And so far, what I've discussed is just the absolute simplest case, which hopefully will, serve as some sort of blueprint. But there's many directions to explore, and hopefully we're able to generalize this story along all these different axes. The question of non-invertible symmetries in particular is, I think, going to be quite a challenge, but an interesting one at that. So yeah, thank you for your attention.
Great, thanks very much for this nice talk. Other questions? So could you go back to this discussion in your first part where you were saying this paper that you wrote with Levine and also Caroline and others, where gaugeability is not based, it's the same as onsiteability, but it is stronger than being anomaly free.
Yeah.
Yeah, could you say a bit more about this, please? Sort of how one should think about that as then the onsiteability as sort of something that, because your goal was at the beginning trying to characterize different phases or distinguishing different phases. So if essentially, right, in this particular case, you have maybe obstruction to onsiteability, but there's really not an anomaly. So could you discuss then in what sense this has implications on distinguishing phases or IR properties?
Right. So the the key point is that there is some obstruction to onsiteability, which is not an anomaly in the sense that this
It's not a
obstruction.
Taft anomaly. Yes, I know.
Yeah. So I guess you're familiar
So I'm
with
saying, what is the physical implication of that? That's
of
my
this
question.
particular H2 obstruction.
Yes.
That I don't have an answer for that.
Because in these cases that you discussed, there seems to be sort of some relation between actual anomaly. When you say anomaly for you, I mean Taft anomaly, right? I imagine in some shape or form, right? That's how you argued for this. But in that case, it seems less clear.
Yeah. So I would say that as far as we know, there really are no implications in the IR that the presence of such an H2 obstructed symmetry would imply, and so that's sort of really the reason that we did not want to call this obstruction an anomaly. And one point which is probably worth noting is that if one allows for ancillary degrees of freedom that are infinite dimensional,
Oh,
then that obstruction vanishes entirely. And
interesting.
so,
Mhm.
yeah. Now it is possible, and this was explored more in this other work, that there are implications for if you look at higher energies, there are possible implications, which I won't say too much about because it's not something that we studied. But as far as implications for low energy dynamics, as far as we know, there aren't any, and that's sort of consistent with this idea that this obstruction actually vanishes. Yeah. So.
Okay, thanks. Yuan?
I have a slightly technical question. So in your slide, you complicated diagram like for F and R. So even for the very simple pentagon or hexagon equation, your step is very long. I guess you need to make sure the fusion only happening at the J point. So the location doesn't matter. So do you design this process by hand? If I try to generalize into higher dimensional excitation like a loop or membrane, is there any feasible way to write down a similar diagram, like a
So
fusion of loop or fusion of
are you
membrane?
using like this definition of the R symbol here, or
Yeah. So any way to generalize this to for example 3D with loop excitation.
um, presumably there is, but it could be complicated. What might be worth mentioning is that so here I just sort of define the R symbol in this way, but one could alternatively do something analogous to this F symbol where one sort of defines some naive function, like some naive R symbol, and then you could define the actual R symbol as some ratio, something like this. And so for generalizing to higher dimensions, something like this may be more amenable, because the kind of the complexity of the definition is sort of tucked away in this ratio rather than, some complicated geometric thing. But I haven't thought too much about
Yeah, because I think we can try 10J symbol or 15J symbol. Have you considered that part?
Yeah, so for like zero form symmetries in 2+1D, the anomaly is characterized by this 10J symbol, and in a different upcoming work with Kyle and Michael, we sort of we come up with some way to define the 10J symbol. Yeah, we actually use we do it in two different ways. One which is sort of more analogous to this ratio approach, and one which is more analogous to this kind of brute force cancellation approach. What we find is that it is much more convenient to do something akin to this ratio, because I think the process that we sort of the single shot process that we came up with that to define the 10J symbol is something like 45 steps or something like this, whereas yeah, using some kind of ratio like this is a lot cleaner, I'd say. So.
Yeah, thank you.
Okay, any other questions? Okay, if not, let's thank Wilbur again, and we'll see you next week for the last one before Christmas with Fabio Pruzzi. All right, thanks a lot. I'll stop the recording.